This is Radio TV Phono Nut, and we have a Newcomb model AV7 tube type classroom record player from 1964. This is one of the few models that they made that does not have a power transformer. This uses two 50L6 output tubes and push-pull and a 12 AV6 driver tube. And let's turn it on and see what happens. Yeah, you can see we're kind of sluggish there. It'll come up to speed in a minute, which means the motor is all gummy and needs to be taken apart and lubricated. Hearing some sound from the amplifier. Let's put it on a record and see what happens. And as you can hear, we have Distortion City here. Besides the usual mechanical problems, but I'd like to get the distortion out of the amplifier first. Now, there's several things that can cause distortion in a tube amplifier. You can have a leaky coupling capacitor that allows DC voltage to make its way to the control grid of the output tube. You can have a gassy output tube, but usually those don't show up until after the tubes have warmed up for a few minutes. Or you can have an inoperative, in the case of a push-pull circuit, you can have one of the stages in the output circuit can be non-operational. An example of that would be if one half of the winding is open on the output transformer, you won't have any B+ voltage on one of your output tubes, and that can cause this problem. I certainly hope that's not the case here. But yeah, this drive mechanism definitely needs the usual cleaning and lubrication. Yeah, that center bearing needs some lubrication in the worst kind of way. Here's the amplifier. You can see our capacitor is date-coded the 22nd week of 64. Looking under the chassis, we have a few suspect capacitors. It may be bad, those black cat capacitors. But before we jump in and change them, we're going to check some voltages on the output tubes. I'll start with the plate voltage. And if we have adequate plate voltage on both tubes, then that will confirm that the audio output transformer is good. Okay, let's apply power and see what voltage we have. The plate will be pin 3 on the output tubes. So let's do this. Let's keep an eye on the meter. See what we have. Tube number 1. That's good, 148 volts. And tube number 2. That's good, 147 volts. So the output transformer is okay. Now we'll check our screen grid voltages. That'll be pin 4. $125. That looks reasonably okay. And that looks reasonably okay on that tube too. This is kind of a weird circuit. We'll take a look at the schematic shortly, but usually in a push-pull configuration there would be a dual triode tube ahead of the output tubes. One section would be your driver and the other section would be your phase inverter, but in this set they're only using a single section tube, a 12 AV6 as your driver, and the phase inversion is done sort of unconventionally. With one tube they're feeding a signal to the grid, and in the other tube they have the control grid grounded and they're feeding the signal through the cathode. So I'd like to check some voltages there and make sure no positive voltage is leaking to our output tubes, because that can cause distortion. Okay, all of our output tube voltages look okay. So let's check the plate voltage on the 12 AV6. Let's see what we have here. We have 35 volts. That might be a tad bit low. Let's move back to the other side of this plate load resistor right here. Let's see what voltage we have on the other side of this resistor. We only have 46 volts there. Okay, and then that goes back to this filter condenser here through this resistor right there. Kind of hard to do all this with only two hands. Okay, 46 volts there. Let's see what's on the other side of that resistor. 126. Okay, here's the schematic, and we're interested in this last capacitor here. Actually, they have a 40 and a 20 wired in parallel to give us 60, and the voltage is low there. Should be 65 volts on our plate of the 12 AV6, and I believe we were measuring somewhere around 35, and the voltage on the other side of that plate load resistor was also low. Should be about 130. Well, I have the capacitor disconnected and connected to our capacitor tester here. We're reading about 100 microfarad, which is higher than what we should be reading. There we go. Let's check it for leakage. And you can see the light is staying on an extended period of time, which means that section of that capacitor is leaky, and that's likely what's bringing our B+ voltage down. Here's a new 68 microfarad capacitor connected to the tester, and it's reading about what it should. Now let's see what it does as far as leakage. See, the light comes on for a couple of seconds and then goes off. That's what it should do. Let's bring this back down and discharge this. And since one section of the multi-section capacitor can is bad, we'll go ahead and replace all sections. That's just standard procedure. Now, some people are probably wondering, because a lot of people think that when an electrolytic capacitor goes bad, the byproduct is excessive hum in the audio. Well, that's not always the case. Most likely what's going on here is the majority of the hum is being reduced by these two capacitors on the front end that are probably still somewhat good, and then this capacitor on the end here is what's choking our voltage down because it's leaky. Okay, I have the old capacitor disconnected and I'm checking the other sections. We're checking the first 60 microfarad section. It actually reads close to what it's supposed to read in value. Now let's check it for leakage. And as you can see on that one, the light stayed on for a couple of seconds and then it faded out, which is what it's supposed to do. Now the 40 microfarad section. And that seems to be about right. Leakage test. And that's what it's supposed to do. However, on this other section, the light just comes on and stays on, which means an excessively leaky capacitor. So my theory was correct. The first two sections were okay in filtering out most of the hum. The final section is leaky and choking down the B+ voltage. And what we'll do is mount this terminal strip to the chassis. That'll give us a secure location to install the new capacitors, and since our modern capacitors are so much smaller than the originals, they will fit under the chassis without getting in the way of anything. And in order to install the terminal strip. First we have to make sure our area to be soldered to is clean, so I've sanded down both the chassis and the lugs on the terminal strips that we'll be soldering to the chassis. And then we'll need to use a higher wattage soldering iron. This little thing here won't quite cut it. Or I guess it might if I wanted to hold it on the chassis for the next 5 years to get it hot enough. Okay, we're making progress here. We have the terminal strip installed. We have the 2 new resistors installed. This is our diode going straight to where the first filter capacitor is going to go. And this is our red lead going into our output transformer. We move over here to where the second filter capacitor is going to go. And we have our yellow leads going to our screen grids of our output tubes. This lead here originally was not long enough, so I just added a new piece of wire. I just really don't like splicing leads. It just looks sloppy. And then finally on this third filter capacitor, the one that was giving us trouble, here's our line running down here to provide plate voltage to the 12 AV6. Now before I install the 3 capacitors on the terminal strip, I'll go ahead and get rid of this capacitor here. This is our chassis isolation capacitor. One end connects to B-, the other end connects to the chassis. And then we have another such capacitor here, and one end of that connects to the negative side of the cartridge, and the other end connects to B-. So we'll replace those with modern capacitors, and then once we get that done, we'll install the filter capacitors. Okay, we have everything installed and ready to go. Now we're ready to apply power and make some voltage measurements. According to the schematic, we're supposed to have 150 here, 137 here, and 133 here. So let's see if we have those voltages. Let's watch the meter. First capacitor, 153. That's good. Second capacitor, 138. That's good. And third capacitor, 134. That's good. Now let's check our plate voltage on the driver tube. What was it? 35 volts before we started. Let's see what it is now. Well, it would help if I check at the right resistor. 64 volts. Well, the schematic call for 65. We're not going to worry about a half a volt there. Okay, let's put it back together and connect the speaker and see if our distortion goes away. I thought we better get another record because the copyright police might not like me playing Aretha again. So let's check out Nat King Cole. We have some action. Oh, that's better. Bend a little my way. Lean a little my way. Nothing wrong with that. Okay, so just to recap what was going on here, the original problem was distorted audio. And after making some voltage measurements, we determined our B+ voltage on the plate of the 12 AV6 was running way low, about 35 volts as I recall, when it's supposed to read 62. We measured at the other end of this, I believe it's a 330 k-ohm resistor in the plate circuit. Voltage was still low. It's supposed to be 123 volts. It was way under that. And the voltage on the other side of this 22 k-ohm resistor was actually kind of in line with what it should be. So that tipped me off to the fact that these final electrolytic capacitors, that they actually have 2 in parallel to make one, was leaky and choking the voltage down. And that was indeed the case. The capacitor was acting more like a resistor than a capacitor. And once we replace the capacitors with nice fresh ones, our voltage jumped back up to what it should have been, and the distortion went away. So as far as I'm concerned, this amplifier is fixed, and we can move on to the mechanical end of it. Now, I tested these two Black Cat capacitors, 0.047 at 600, and at full working voltage they have just a tad bit of leakage, not nearly as bad as I expected. But given the application that they're in, I just decided to go ahead and replace them with modern AC safety capacitors that are not supposed to ever short. Okay, we're all cleaned up and running good now. I decided not to show that process because it's basically just a repeat of what we've done 1,000 times in the past. And yes, we used our standard non-vaginal phonograph lubricant, as well as our rubber renew in the process. I also replaced the original 81T cartridge and needle combination, which cross-references to an 89T. This one still works, but the tip was worn and it really didn't sound that well. And I reluctantly replaced it with one I had on hand that's a dual LP tip cartridge. The older style cartridges with LP tips on one side and 78 tips on the other side are getting very hard to find. And in today's world, you either have to buy the red LP only version or the green 78 only version, and I just really don't like that. Honestly, I was surprised that the old cartridge had any tip at all left on it, because it seems like most of these school record players that I find, the tip is so badly worn down that it skates across the record. And in some cases, I find a coin taped to the tone arm to compensate for that. So this tells you that most schools didn't replace the cartridges until it was absolutely necessary, and that's not a good thing, because like I've read before, when the audio quality is bad due to a worn stylus tip, it's already done damage to your records. Okay, let's give it a shot here and see what we sound like. Here we are with an LP.
Tuesday, I'm so tired, got no time to play. Here come Wednesday, I'll be to my side. My gal called, got to tell her that I'm out. 'Cause Thursday is a hard working day, and Friday I'll get my pay.
Okay, well that's about all I've got for this. The 1964 Newcomb record player is back to life and should be good for another few decades. Okay, thanks for watching, and more later.